So welcome all. This is week 5 tutorial for the course Basic Linear Algebra taught by Professor Inder Kumar Rana. I'm Pintu Kumar. I'm a PhD scholar at IIT Bombay. Today I plan to cover eigenvalues and eigenvector and how do we check whether a matrix is diagonalizable or not. And if it is diagonalizable, what beautiful properties come along with it. We'll have a look at these aspects and we'll solve question along these lines. So topics that I plan to cover today are eigenvalue, eigenvector, and diagonalizability. Okay, so like throughout the course, like one most common thing that you would have seen is this kind of system of equation that you have to solve. So almost most of the theory in linear algebra revolves around solving system of linear equation, right? So if you look at these two matrix representation, so which one do you feel is more easier for you to solve? So this one has only entries at diagonals. This one has entries almost everywhere. So which one do you feel is like more easier for you to solve? For me, if I look at this equation, I can directly tell that my x is 3 and y is 2. Whereas in this, I will have to eliminate or do an extra step of, let's say, row echelon form and then look at what is the solution. The y is 4. Okay. So if you have a matrix representation for some transformation that is in diagonal form, then solving system of equations or these kind of things become pretty easy for you, right? So why diagonal representation works is that it is easier to work for you. Another thing is like when you solve a real world problem using linear algebra, when you have very large number of variables, then solving an matrix takes space on your PC or those kind of things and have computational aspects related to it. So these diagonal matrices are very easy to store. You just need to store one like array of value and you are done with it. So diagonal representation of any matrix is very useful in this context. So the question that we should be asking over here is like, does there exist basis beta? So last time, I think in week 3, Professor Rana covered, and last time I also covered, that if you have different basis vectors, you will have different matrix representation for same linear transformation, right? So the question that is being asked over here is like, does there exist a basis beta such that the matrix representation of a linear transformation with respect to that a basis is a diagonal matrix? Okay, this is the question that we would be answering today. And the next part of the question is, if it does exist, how do we find it? Okay, so let's look at just a very brief recap. That let's say you have a linear transformation from V to V, okay, and you have some basis beta. So how do you write its matrix representation? Very brief recap. Let's say this is beta 1, beta 2, beta 3. Okay. First thing that you do is you find the map of T of beta 1. Okay. Let's say it came out to be V1, something you obtained out of it. Okay. Then you write V1 in form of all these beta 1s, alpha 2, beta 2, and so on. You will write something like this, right? And what would be the first column of the matrix that you will obtain? First column would be alpha 1, alpha 2, and so on, alpha n. So this is how your matrix representation works. Okay. Now, if we want, sorry, yeah, if we want that this matrix representation, that whatever we are finding should be a diagonal matrix. So what do we want? We want these entries to be 0. Okay, so in column 1 we only want this entry. Okay, so what does that mean? That we want T of beta 1 only to be some alpha into beta 1. We just want this corresponding component. Okay, similarly for other vectors also, like we want this entry to be non-zero, rest to be 0. So that would imply T of beta 2 is equal to alpha 2 into beta 2. This is what we want in some sense. Okay, so now, so from here we can see like how did we reach to a definition of eigenvalue or eigenvector, how it is motivated. So if you have a non-zero vector v, because why are we focusing on only non-zero vector, is that we are looking for a basis, and basis elements are always linearly independent. So we can't have zero vector in there, right? So if there exists v non-zero such that T of v is some lambda times of v, it is similar to this thing that whatever we gave it as an input, it is just giving the same thing as output with some scaling. So this lambda over here is a scalar that belongs to your field. So what we want is that T of v is some lambda times of v. Then in this kind of situation, your v is called a eigenvector, and this lambda thing is called your eigenvalue for this transformation T. Okay, and like whenever you talk about eigenvector, that eigenvector is always associated with some eigenvalue. So this v is associated with this eigenvector, eigenvalue lambda. Okay, so now getting back to our question that we were asking is whether we can have a representation beta or not, so that your T of beta is a diagonal matrix. So one answer that you know to is that if you have sufficient number of vectors satisfying this property lambda v, so that you can form a basis out of these kind of vectors, then you will have this kind of representations. Okay, then this will hold. So here is just a very formal definition of eigenvector. This is same as what I told you, but just to read it in a formal way. So if T is a linear operator, by linear operator we mean T is a map from same vector space to same vector space. That is what is called a linear operator. Okay, so if you want to look at something like a diagonal matrix, so you want entries on all the diagonals. So a diagonal matrix can only be of size n cross n. So the number of columns and rows should match. So that's why we are just focusing on linear operators rather than linear transformation. Okay. So if T is a linear operator on a vector space V, a non-zero V is called the eigenvector of T if there exists a scalar lambda such that T of V is equal to lambda times V. The scalar is called eigenvalue corresponding to the eigenvector. Any doubt in definition of this eigenvalue? Okay, hope that I was clear. So let's try to solve an example based on this. Okay, so let's say you have a matrix given by A is equal to 1, 3, 4, 2, right? Now you are given with two vectors. You have to check if v1 and v2 are eigenvector, and if they are, you have to find their eigenvalues. Okay, so let's say we have 1, 3, 4, 2. What we want is, okay, let's say we have v1 as a vector if it is an eigenvector, then T v1 would be some lambda times v1, right? So if we talk about matrix representation, then T of v1 is nothing but A times of v1. So if you want to find transformation of some vector, you just multiply that vector with a matrix representation. So this is 1, 3, 4, 2 times, what is v1? 1 comma minus 1. So what do we obtain? We obtain 1 minus 3 as minus 2, 4 minus 2 as 2. So what it is? This is minus 2 times of 1 comma minus 1. So what does this show? This shows that this v1 is an eigenvector with eigenvalue minus 2. Okay. Now, if we look at the next part, that is v2 is 3 comma 4. Okay. So let's multiply this thing 1, 3, 4, 2, 3, 4. I think this is 3, 4. Yeah. So we obtain 3 plus 12, that is your 15, and we obtain 12 plus 8, that is your 20. So what it is? You can take 5 out and you get 3 comma 4. So this is also an eigenvector with eigenvalue 5. Okay. So this was to verify whether a vector is an eigenvector or not. We will later see how do we find this eigenvector or eigenvalue in the first place. Okay. So one more thing, if you find this like this thing, so like you know now that 1 minus 1 and 3 comma 4 is are eigenvectors, right? Then one thing that you should know is that if you take this as your basis, this set beta as your basis, and you form this matrix representation for this particular transformation, then that would be a diagonal matrix. And how would that matrix look? That would look something where your diagonal entries are your eigenvalues. So first one is minus 2, second one is 5. So it would look something like that. So with respect to this basis vector, you will find this particular matrix representation for your linear transformation. Okay. So now let's try to look more closer into it. Like how can we obtain? So now you know that does there exist we have answered sort of the first question that we asked, does there exist a basis? So next thing is how to find it. Okay. So how do we know there exists a basis? So if we have sufficient number of vectors satisfying TV is equal to lambda v, then there exists, otherwise there doesn't. Okay. Now how do we find it? Let's see. What do we want? We want that T of v should be equal to lambda v. Okay. If we take this thing on the left hand side, what do we get? We get TV minus lambda v is equal to 0. We can take the vector v outside, so this we will get as T minus lambda I v is equal to 0. Okay. What do we want is that our v should be non-zero, right? What we want, our v to be non-zero. When does a system of equation, let's say we have a system of equation ax is equal to 0 and ax is equal to has, let's say ax is equal to 0 has a non-zero solution. What does that mean? That means your A is a non-invertible matrix. Why? So if A would have been invertible, then you could have got x is equal to A inverse of 0, which is equal to 0. So if A inverse exists, then only solution you have is x is equal to 0. Okay, but we want V to be non-zero. That is, this matrix should not be full rank, or in other words, this should not be invertible. Okay, so what does this mean? That T minus lambda I is not invertible, which further means that determinant of your matrix A minus lambda I is 0. Okay, so we would be using this particular thing or the formula that we have written over here to find our eigenvalues and later find our eigenvectors. Okay, this particular relation is very important. Also, to mention that what I said, that determinant of A, or let's say T was a better notation, T minus lambda I is equal to 0. If you just look at the left hand part of this equation, this is a polynomial. This polynomial is called as the characteristic polynomial. Stick polynomial of your transformation T. Here is a formal definition. If A is a n cross n matrix, that is T is a transformation from V to V, where V is n dimensional, the polynomial determinant of A minus T I n is called the characteristic polynomial of A. Okay, I n is your identity matrix, if I didn't mention it before. Okay, so yeah, this is something known as matrix. So we had an example over here, that is 1 3 4 2. Let's try to find the this characteristic polynomial for this. So if A is your 1 3 4 2, what we want? We want determinant of A minus lambda I. What it is? This is determinant of this matrix 1 3 4 2 minus lambda is this identity matrix is 1 0 0 1. If you multiply it by lambda, you get something like this, right? So we want its determinant, that is 1 minus lambda 3 4 2 minus lambda. This you obtain as this is equal to 1 minus lambda into 2 minus lambda minus 12. What it is? So lambda square, and here you get minus 3 lambda plus 2 minus 12, that is lambda square minus 3 lambda minus 10. Can we split it up? We'll try to split it up also. We can, right? So this would be lambda square minus 5 lambda plus 2 lambda minus 10. This is equal to lambda minus 5 plus 2 lambda minus 5, which is lambda plus 2 into lambda minus 5. Now, if you remember, when we look at this particular thing that I mentioned is very important to this particular thing that I said is very important to remember. So in order to find your eigenvalues, you should use this like formula. The determinant of A minus lambda I is 0. So we already found this determinant of A minus lambda I. If you want to find the eigenvalues, let's say what we want to do is determinant of A minus lambda I is equal to 0. This we already found. So if we equate it to 0, what all do we get? So lambda is equal to minus 2 and lambda is equal to 5. This is same what we obtained over here also, if you can cross check that we obtained one of the eigenvalues as -2 and another one as 5. Any doubts till now? You have to ask anything in Hindi, English or anything. अगर इंग्लिश में नहीं समझा हिंदी में भी पूछना हो कुछ. Okay, right. So we have one more question. I'll give you 2 minutes to try to solve it, because the tutorial session, it would be better for you also if you get your hands dirty with it. Then I'll start solving it. So I'll wait till 8:28 and see if you can solve it. Probably I'll give you a hint. So what we want to do is we want to do determinant of a minus lambda I is equal to 0, and we want to find the values of lambda satisfying this thing. So what we want to do is 1 minus lambda 1 4 1 minus lambda equal to 0. We just need to solve this determinant. What we obtain? We obtain that 1 minus lambda square minus 4 is equal to 0, or in other words 1 minus lambda square is equal to 4. What does this mean? 1 minus lambda is equal to plus minus 2, and we can get value of lambda as either 1 minus 2 or 1 plus 2. So what do we get? Lambda is -1, or lambda is equal to 3. Right, so our eigenvalues are -1 comma 3. Okay, let's take a slide. Yeah. Hello. Okay, so here we have P2R. I think you would be probably aware of what is P2R. P2R is polynomial of degree up to 2. Okay, so this is the transformation that is given to us, and beta is the standard order basis and a is t of beta. Then we have to find eigenvalues for this thing. Okay, so first of all, what is the standard basis for polynomial up to degree 2? This is 1 x comma x square. Okay, we'll try to find the matrix first, this A matrix. So T of f of x is given as f of x plus 1 into f dash of x. Okay. So what is t of 1? T of 1 would be 1 plus x plus 1 into 0, which is equal to 1 plus 0 times x plus 0 times x square. Okay. Similarly, let's look at t of x. This is equal to x plus 1 into f dash x, that is 1. Now this is equal to 1 plus 2x plus 0 times x square. Okay. Now t of x square is given by x square plus x plus 1 into 2x. This now you get to 0 times of 1. You don't have any constant term now. Okay, so you can expand it like x square plus 2x square plus 2x, right, plus 2x plus 3x square. So if you write it in a matrix notation, how do you get it? You get something like, so this coefficients of first image is your first column, that is 1 0 0, 1 from here, 0 from here, 0 from here comes here. Okay, and now the second term is 1 2 0, third one is your 0 2 3. Okay, we have to find eigenvalues for this particular matrix. Let's see how we can do it. Like, we already know how we have to do it, we just need to do it. Okay. Okay, so again, same thing we have to do, that determinant, let's call this as A matrix, then determinants of A minus lambda I should be 0. This is what we need to see, right? So let's write it in this form. This would be 1 minus lambda 1 0. Now I over here is 3 cross 3, just a reminder. This entry remains as it is, 2 minus lambda 2 0 0 3 minus lambda. Okay, let's evaluate this determinant with respect to the first column. So what do we obtain? This is 1 minus lambda, right, multiplied by determinant of, so you cover this row, 2 minus lambda 2 0 3 minus lambda. This is nothing but 1 minus lambda into 2 minus lambda into 3 minus lambda minus 0 into 2, which is obviously 0. So this factors very well as 1 minus lambda into 2 minus lambda into 3 minus lambda. And what do we want to do? We want to equate this to 0. So what are the values of lambda that we get? We get 1, 2, 3. So this is our eigenvalues. Okay. Now one small tip for you, like I already knew what are the eigenvalues as soon as I saw this matrix. You can also do that. How can you do that? So if you have a upper triangular matrix, okay, upper triangular matrix, how does an upper triangular matrix look like? You will have some entries on the diagonal, you will have some entries over here, you can have 2 3 anything over here, but everything below the diagonal is always 0. Okay, if you have something like this, then entries on diagonals are your eigenvalues. Okay, for example, in this example we had 1 2 3 on the diagonal, so its eigenvalue were 1 2 and 3. Okay. Okay. So now we will move one step forward and try to find eigenvector. Till now we were only finding eigenvalues. Now we have to find also the eigenvectors. Okay. Just a quick recall that a non-zero vector V satisfying this kind of relationship is called eigenvector. So finding eigenvector is a two-way process. It's a two like process thing. So in order to find eigenvector, the first step is to find eigenvalue. Okay. And the second step is to find eigenvector corresponding to that eigenvalue. I'll show you how. Corresponding eigenvector. This is a very simple matrix given to us, that is where A is pretty simple, 1 1 4 1. So you first need to find its eigenvalues. Okay. So in order to find the eigenvalue, what you need to do is, again, determinant of 1 A minus lambda I is 0. So this particular example we just did, so this is 1 minus lambda square minus 4 is equal to 0. I think this was the exact same. Yeah. So what did we get as eigenvalues? We got minus 1 comma 3. So its eigenvalues are 1 minus 1 comma 3. So you will get eigenvectors corresponding to every eigenvalues. So there will be different eigenvectors corresponding to different eigenvalues. So let's say if you want to find eigenvalue for lambda is equal to minus 1. So we will get back to the property that it satisfies. What does it satisfy? It satisfies A minus, okay, it satisfies AB is equal to lambda V, right? Or in other words, it satisfies, because this is a non-homogeneous equation, you can solve this also. But the simpler one is to solve that A minus lambda I times V is equal to 0. Now, this is what we obtained earlier also, but now over here we'll put the value of lambda. So for lambda is equal to minus 1, if we have to solve, then this is 1 minus 1 is minus of minus, this you will get 2 over here if you put it over here. Okay, I'll probably write it just one more step. I know it's trivial, but I'll probably write it. Okay, so this is A minus lambda I would be 1 minus lambda 1 4 1 minus lambda into something as v1 v2 is equal to 0. This is what you want to see. Now your lambda value is minus 1, so we can replace minus 1 over here. What we obtained? We obtained 2 over here and another 2 over here. Okay. Now what we can do is we can try to make this element as 0. In order to make that as 0, how can we make it? R2 goes to R2 minus 2 times of R1, and we obtain here a system equation as 2 1 0 0 v1 v2 is equal to 0. What do we obtain? 2 v1 minus plus v2 is equal to 0, or v2 is equal to minus 2 times of v1. One thing to remember is that if you are looking for an eigenvector, right, let's say v is your eigenvector, okay, then t of v is lambda v. Now take 2 times of v, then what would be t of 2v? This would be 2 times of t of v, that is 2 lambda v, right? Or this is nothing but lambda times 2v. So if your V is your eigenvector, then any scalar multiplication is also an eigenvector. Okay. So you will not get a unique eigenvector, right? You will get probably one linearly independent eigenvector if you have only this eigenvalue occurring only once. But that doesn't guarantee that your eigenvector will be unique. In fact, it will never be unique, right? You can just multiply with some scalar and get another one. So you will always get this kind of relation, and you can pick any vector satisfying this equation. Okay. So let's say if I take some value for your v1, let's say I take v1 is equal to 1, then what would my v2 be? v2 would be minus 2. So 1 minus 2 is a is important over here. This is not the only eigenvector, but a eigenvector or an eigenvector for lambda is equal to minus 1. Okay. Similarly, we had one more eigenvalue, that was 3. We can find eigenvalue for lambda is equal to 3, right? I'll change the pen color. For lambda is equal to 3, what we need to do is 1 minus lambda, again the same thing. We just put lambda is equal to 3, so this would be minus 2. This would be minus 2, 1, 4 minus 2, v1, v2 is equal to 0. What does this imply? This implies, again you can make this entry as 0 by adding r2 goes to r2 plus 2 times r1, then this become minus 2, 0, 1, 0, v1, v2 is equal to 0, or 2v1 minus 2v1 plus v2 is 0. This implies v2 is 2 times of v1. So another eigenvector that you get is, from here you can just take your v1 to be 1, v1 is equal to 1, then v2 is 2. So your eigenvector is 1 comma 2. Okay. So what is the set of eigenvectors that you got? So you got your set of eigenvector as 1 comma minus 2 and 1 comma 2. Right. So this is how you find your eigenvector and eigenvalues. Okay. Any doubt with it? Okay. Moving ahead, we will be solving some more example on the same. So here we are given with a transformation. Okay. And you can also try solving along with me so that we can cross check our answers. We have to determine the eigenspace of T. That is, you have to find eigenvectors. Okay. And the basis that you have been asked to construct A is the standard basis for all R3. So what is standard basis for R3? This is nothing but 1, 0, 0. This is 0. 0, 1, 0 and 0, 0, 1. Okay. So this is the standard basis of R3. First thing that we have to do over here is that we have to find the matrix A. Then we again have to do all these things to get the eigenvalues as well as the eigenvectors. Okay. So let's start by finding the image of T of 1, 0, 0. This would be 4 plus 0, so it would be 4. 2 plus 0, So 2 and 1. So one benefit of having things in standard ordered basis is that you need not write it in terms of sum. You actually know, like, it's v1, if it is v1, v2, v3, then this vector is 4 times v1 plus 2 times v2 plus 1 times v3. This is quite clear. Okay. Now let's find t of 0, 1, 0. What it would be? It would be, now the first term becomes 0 because there is no a2 in it. Second term becomes 3 and third term again becomes 0. Let's find the third one, t of 0, 0, 1. You get 1, 2 and 4. So how does this a look? A looks something like 4, 2, 1, 0, 3, 0 and 1, 2, 4. Okay. Okay. So now what we have to do is we have to again find determinant of a minus lambda I is equal to 0. That would mean 4 minus lambda 0, 1, 2, 1, 3 minus lambda 0, 2, 4 minus lambda. This thing is 0. So you can see that the second row over here, right, has only one non-zero entry. So it is best to evaluate this determinant along that. So this, if this is plus, this is minus, this would be plus, right? So this would be 3 minus lambda. Now this thing gets striked off. So this is 4 minus lambda square minus 1 is equal to 0. So this implies 3 minus lambda, and this is lambda square plus 16 minus 8 lambda minus 1 equal to 0. This implies 3 minus lambda, lambda square minus plus 15 minus 8 lambda is equal to 0. This implies 3 minus lambda. We can, how can we reach this thing is by 3 lambda square minus 3 lambda minus 5 lambda plus 15 is equal to 0. Lambda minus 3 minus 5, 3 is equal to 0. So what are the eigenvalues for this particular matrix? So the eigenvalue for this particular matrix is lambda is equal to 3 2 times, because 3 is occurring 2 times, then this lambda is equal to 3 is 2 times. Another eigenvalue is lambda is equal to 5. Okay, we will not solve for eigenvector corresponding to lambda is equal to 5, but because lambda is equal to 3 is occurring 2 times, let's see does it have anything special with it or not. Okay, so to find eigenvector corresponding to lambda is equal to yeah, corresponding to your lambda is equal to 3. What we should do is, we should do a minus lambda I times v is equal to 0. Okay, so your A matrix is this. So A minus 3I would give something like, so let me copy this matrix first. Yeah, so your A matrix is given out to be something like this. So A minus 3I would look something like 3 would be 1 0 1 2 0 2, and this would be 1 0 1. Okay, if we do just one simple operation, we want, right, wait, first let me write. So we want this times v1 v2 v3 going to 0. Okay, so if we just do one simple operation, that r2 goes to r2 minus 2 times r1, and r3 goes to r3 minus r1, what do we obtain? 1 0 1 0 0 0 0 0 0 v1 v2 v3 is equal to 0. What does this give? This gives us v1 is equal to minus v3, and v2 is free. Okay, now as you saw that lambda is equal to 3 was occurring 2 times. Okay, and here how many choices you can make? W2 is already free, right? And you can make one choice over here also, so its solution space definitely has dimension 2. So if you have this kind of situation, when you have more than one dimension, then you try to write those many number of linearly independent eigenvectors. Okay, so let's say for the first one I chose v2 is equal to 1 and v1 is equal to 0. Let's say I'm making choices for v2 and v3. That would make v3 is equal to 0 automatically. So one of my eigenvector is this. In second case, let's make v1 is equal to 1 and v2 is equal to 0. That would make 1 0 minus 1 as another eigenvector. So this set is an eigenspace corresponding to lambda is equal to 3. Okay. Okay. Now we have reached to the point where we should talk about when should a like matrix be diagonalizable. But let's talk in very simple informal way first. Okay, so how will you know that like you have a diagonalizable matrix or not? Okay, so whatever the case is, initially you will be given with some matrix A. Okay, what is the first step that you always do? You find its eigenvalues. Okay, now let's say this vector space is our set of real numbers. Okay, if it is over set of complex number, let's say, then if you try to solve determinant of a minus lambda is equal to 0, you will always get solution for lambda. But if your vector space is over the set of real numbers, then there can be some cases when you don't get solution. For example, it is very easy to construct, let's say this is lambda, this is yeah, let's take this as 0 0, and take this as 1 and minus 1. Okay, so if you try to find do this determinant of a minus 0, this would be minus lambda 1 minus 1. So is equal to 0. This would imply lambda square plus 1 is equal to 0. and solution does not exist in your real space, right? So first step for any diagonalizable matrix is that you should have a zero, or you should have eigenvalues in that particular field. That is the first and foremost thing that you should have. Okay, that you should have eigenvalues in that particular field. So how do you check that? So whatever characteristic polynomial that you have, that should have all the roots in real numbers. Okay, let's say for if you have like real field. Second thing is, now let's say you got lambda 1, lambda 2, lambda n as your eigenvalues. There are two cases that can happen over here. Either all your all your lambda 1, lambda 2, lambda n are distinct. One possibility is this. In that kind of situation, your matrix will always be diagonalizable. Okay. In second case, you can have, let's say, for example, in last case, lambda is equal to 3 repeated 2 times. Okay. Then you don't have distinct eigenvalues. Okay. So for the case when, let's say, some lambda, let's call it lambda 1, repeats k times, then if you get, okay, k linearly independent eigenvectors corresponding to lambda 1, then matrix is diagonalizable. So whatever is the multiplicity of your every eigenvalue, if you get those many number of linearly independent eigenvectors, then you can say your matrix is diagonalizable. Okay. So just to state it in a more formal way, so let's say T is a linear operator, then you call T as a diagonalizable if and only both these condition holds. What is the first condition? First condition says that the characteristic polynomial splits. What does this mean? So a polynomial, let's say P is your something, that splits if you can write it in form x minus a, x minus b, x minus c. So if you can write it in this form, then all your roots belong to that particular field. This is what I told you in first point, that your eigenvalues all must belong to the same field. So the first point would just mean that your eigenvalue exists in that particular field that you are working with. Okay. The second point is, for each eigenvalue lambda, the multiplicity of lambda should be equal to n minus rank of Ti. Okay. So what I said is that you should have as many as multiplicity of lambda linearly independent eigenvectors. This is what I said. You can just say the same thing in this way. So if you have matrix T minus lambda I, V is equal to 0, you want to solve. So whatever is the number of like rows you get in row echelon form, that would tell you the number of linearly independent eigenvectors that you can have. For example, when we were solving this particular example, we had two non-zero rows. That's why two of our variable became free and we got two linearly independent eigenvectors. So whatever is the number of 0 rows in row echelon form of this particular matrix, that will give you the number of linearly independent eigenvectors that you can have. So this thing is stating that thing. So rank is number of non-zero row. But what we want to count number of zero rows. So they have just subtracted n minus number of non-zero rows to get the zero rows. So they are also just stating the same thing, but in a different way. Okay. So just two things to remember. You can ask if you have anything to. You need not raise hand.
Sir, number of independent solutions and number of non-zero rows both are different.
Both are.
Solutions and vectors, sir.
See, you can have more than one solution. Let's say I'll give you a very simple example. Okay, let's say you have 1 1 0 0 and this thing going to 0 0. So how many solution you can have? So anything that satisfies v1 plus v2 is equal to 0 or v1 is equal to minus v2, anything that satisfies this thing is your solution. So let's say you took 1 comma minus 1, you can clearly see that this is a solution. You can take 2 comma minus 2, this is a solution, right? But if you see, these two are not linearly independent. There is like these are multiplicative of each other, like they are linearly dependent. So that's what I'm saying. So you can have infinitely many solutions also, or you can have more than one solution, but the number of linearly independent solution that would remain fixed. Okay, and that number of linearly independent solution that would be given by number of zero rows that you have over here. Okay, I hope I'm clear.
Vectors means eigenvectors, number of independent eigenvectors or solutions.
Yes. So like if you are
Both are
solving,
same.
if you are solving a minus lambda I is equal v is equal to 0, the vectors that you would be getting is your eigenvectors.
Sir, one question, solution, number of independent solution, they calculated independent eigenvectors, they calculated, sir.
Yes.
I have some confusions.
Okay. See, see, I'll explain it to you. See, first point I said is that all eigenvalues must belong to that field. This point is crystal clear, I hope. Then I'll get to the question that you are asking, if this thing is clear.
Yes, yes, sir.
Now, what I'm saying is, second thing that I am saying, we'll get back to see what is written over there, is let's say you have an eigenvalue, lambda is equal to 3. I'm just taking an example, okay? And its multiplicity is 2. That is, for example, we had a matrix over here, probably you joined when we were solving this question. So we had a matrix over here. When we found its eigenvalue, we got 3 2 times. So the characteristic polynomial was something like lambda minus 3 whole square into lambda minus 5 with a negative sign over here. So 3 was occurring 2 times. Okay. So that is what is called as the multiplicity of an eigenvalue. How many times it is occurring. So let's say if a lambda is equal to 3 has multiplicity 2. Okay. Now, how do we proceed to find its eigenvector? We do simply this thing, a minus 3i v is equal to 0. Now, what I am saying is, like if this particular system of equation has two linearly independent solution, okay, that is your multiplicity of your eigenvalue matches with the number of linearly independent solution. So whatever solution you are getting from here is obviously an eigenvector. So that would mean is that you are getting two linearly independent eigenvectors. Then your matrix would be diagonalizable. This is what I'm saying. Is this much clear? Then I'll get to what
Yes,
is
sir.
written
Yes,
there.
sir. Yes, sir.
Okay. Now let's see what they have written. They have just rephrased it in another way. Okay, I'll just draw a space here. Okay, now what they are saying is that the multiplicity should be equal to rank of this t minus lambda I. Okay, so if you look at this matrix t minus lambda I, okay, so what I said is uh, like if you have, let's say, initially you can have anything. If you row reduce it, okay, uh, we talk about rank and those things only when we row reduce that matrix, right? So if you row reduce it and you have, let's say, n 0 rows, okay, let's say this matrix was m cross m, and if you have n 0 rows, then you will get n linearly independent solution for this kind of thing, that this v is equal to 0, linearly independent solution. Is this thing clear? Like if you have n 0 rows in this row echelon, row reduced form, then you will have n linearly independent solution. Okay, and rank is just the opposite. What is rank? Rank is the number of non-zero rows. So they didn't wanted to write it in form of 0 rows. So what they did is they wrote it in terms of rank. Let's I have just used a very bad notation over here. Let's call it j. Okay, we have j 0 rows. So let's say we have total n rows. Okay, and out of which, let's say, m of them are your non-zero rows, because rank is, let's say, m. Then how many are your zero rows? Zero row would be n minus m, right? And what I claimed is that whatever is your number of zero rows, those many linearly independent solution you will get.
Yes, sir.
Now, am I making sense? Is it clear?
Yes, sir.
Okay, thank you. Okay. Okay, so let's look at this matrix and we have to test for diagonalizability. One thing again, we can solve this thing, that is determinant of a minus lambda I is equal to 0 to get eigenvalues.
Eigenvalue 1, 3, 1.
What is eigenvalues? Can you type, because your voice was breaking?
3, 3, 1.
No, it won't be 3, 3, 1. So if you have a, as I mentioned few moments ago, if you have a upper triangular matrix, you see everything below the diagonal is 0, right? So your eigenvalues are nothing but the entries on your diagonal. So eigenvalues would be 3, 3, 4 only.
4. सर
Yeah.
ये
हाँ, वो हिंदी बोल सकते हो, कोई दिक्कत नहीं, बोलो।
ये जो नीचे का एलिमेंट है वो 4 है कि 1?
4 लिखा है, 4।
तो 4 है, तब मेरे लगा कि 1 है तो 1।
नहीं नहीं, वो 4 है, सॉरी अगर ऐसा कंफ्यूजन है तो। दिस इज 4।
मुझे लगा था 1 है, तभी मैंने वैल्यू
ठीक,
1 बोला था, ऐसे तो सॉरी हूँ।
हाँ। Okay, so the eigenvalues are 3, 3, 4. Okay. Now we have to find again the multiplicity of this thing is 2 over here. Okay. So if we have to check the diagonalizability, so we just need to test whether it is diagonalizable or not. So we can just ignore this 4, 1, because there will always, so if you have anything with multiplicity 1, there will always be an eigenvector corresponding to it. You need not worry about it. Okay. So now we will just test for this 3 thing. Okay. So what we will try to do is we will look at the solution space of a minus 3i into v is equal to 0. So if we take a minus 3i, this would become 0, 1, 0, 0, 0, 0, 0, 0, and this would become 1. Okay. So now you see this is already in your row echelon form, whatever we got. And we have only one, you can say, 0 row. So as I said that your number of 0 row should give you your number of linearly independent eigenvectors. So what I'm saying is that we will get only one linearly independent eigenvector over here, because this is our first example. We'll verify that. Okay, so we want to put this equal to 0. What does first row gives? First row gives that your v1 is equal to 0. Sorry, v2 is equal to 0. Sorry, my bad. And the last one gives you that your v3 is equal to 0. Now you can easily see that only free variable left to is v2. So if your v1 is 0, v3 is 0, you can only have element over here. So if you take anything over here, let's say 3, let's say 4, okay, these are all multiples of each other. Okay, if you multiply this thing by 3, you get this. If you multiply this thing by 4, you get this. So how many linearly independent vectors you can have at max? You can have only one linearly independent type, right? But what was the multiplicity of 2? This 3. Multiplicity was 2. So we needed 2 linearly independent eigenvector to infer that this particular thing is diagonalizable. So because we didn't had 2, so this matrix is not diagonalizable. This is not diagonalizable. Okay. Okay. So we can try one more example over here. Okay. So T is a linear operator and P2 is R, as I mentioned, this is polynomial up to degree 2. So its basis can be given by 1, x, x square. So in this example, we'll first have to form a matrix corresponding to this thing and then solve for our whether it is diagonalizable or not. We have to check that. Or like we'll take this example as a full-fledged example, and we'll also find all the eigenvector possible and those kind of things. Okay. Hopefully the calculation don't become ugly. Okay. So first of all, we need to look at the basis. This is 1, x square. Okay. So if we find t of 1, what it is? It is f of 1. So 1 is already a constant, so this is 1 plus f dash of 0. So anything with derivative would be 0. So I'm straight away writing it as 0. So this is nothing but 1 plus 0 times x plus 0 times x square. Okay. Now let's find for t of x. So it says f of 1. So if we put 1 in x, it would be 1 only. Okay. Plus f dash of 0. So f dash of x is 1. Okay. So what is f dash of 0? This is 1 into x plus this is 1. F double dash is 0 into x square. So this is 1 plus x plus x square. This is 1 times x into 1 times x square. Now let's find t of x square. Okay. What is t of x square? Your t of x square is f of 1, that is your 1, plus f dash of x is 2x. At 0, it is 0 into x. F dash at 0, again 0. F double dash is 2 x square. This is 1 plus 2x square. Right. So if we form the matrix representation, what it would be, we take first of all the coefficients from first. So to write it as first column, so this would be 1 0 0. Second column would be 1 1 1. Third one would be 1 0 2. Okay. So this is our matrix A that is given to us. Now we need to find its eigenvalues, eigenvectors, and check for diagonalizability. Okay. Probably this would be the last lengthy example that you will have to solve. Then I'll skip to some other interesting things that I have, and if time is left at the end, we'll solve some other examples. Okay. Okay. So first step, what we need to do is we need to find a minus lambda I determinant. Okay. We have to equate it to a 0. What would it give? This is 0 because we are sorry. This is 1 minus lambda 1 1 0 1 minus lambda 0 0 1 minus lambda 2 minus lambda. This is equal to 0.
1 1 2.
What it is? What did you get? You can repeat, your voice was not clear, that's why I'm asking.
सर थर्ड रो में 1 माइनस लैम्डा क्यों आएगा?
हाँ वहाँ गलती है, it would be 1 only. ठीक है.
ओके सर.
हाँ. तो हाँ, let's see what. So we have to find its determinant. In our first column we have only one non-zero entry, so we can evaluate using that. So it is 1 minus lambda. So that blocks are this row and this thing. So that would be
सर आंसर 1 1 2 आएगा.
हाँ, this is 1 1 2 ना.
सर
हाँ, तो आइगन वैल्यूज आ गए हमारे 1.
सर क्योंकि ये लोअर ट्रायंगुलर की तरह वर्क कर रहा है, मतलब अपर.
हाँ, मतलब अगर इसको हम वैसे शिफ्ट कर दें तो हो जाएगा. ठीक है.
ओके सर.
ओके, तो अब 2 के लिए सबसे पहले अब आइगन वेक्टर निकाल लेते हैं. We'll find eigenvector corresponding to, I think there is one guy who is not very comfortable with Hindi, so I'll keep going in English. So yeah, so we'll first find corresponding to lambda is equal to 2. Okay, so if we have a something like this, so if you want to do a minus 2i v is equal to 0, how would it look? This would look like minus 1 1 1 0 minus 1 0 0 1 0. ठीक है. v1 v2 v3 is equal to 0.
v1 equal to v2. सॉरी सर, v1 equal to v3 है.
v1 is equal to v3
v3
और एक कुछ 0 भी बनेगा ना, v2 शायद 0 बन जाएगा.
सर v2 equal to 0.
हाँ, so we can just make this entry as 0 by adding this thing, then that would give us v2 is equal to 0, and from first one we'll get v1 is equal to v3. So what can be a possible option? Possible can be 1 0 1, right? So this is वो साउथ वाला बा. So we'll have 1 0 1. Now the case is for when we have eigenvalue as lambda is equal to 1. Let's see what happens then. Okay, so then we will have 0 1 1 0 0 0 0 1 1. Again we can make this as 0 1 1 0 0 0 0 0 0. That is v1 v2 v3 is equal to 0. Okay, so we can see the relation v2 is equal to minus v3, right? This is what you got, or you got something else?
सर इससे v1 तो नॉट डिफाइंड है.
नहीं समझा.
सर v1 इसमें v1 की एंट्री हम यूज नहीं कर सकते, तो v1 नॉट डिफाइंड.
हाँ, v1 हमारा फ्री वेरिएबल हो गया. हाँ, फ्री हो गया. हाँ, नॉट डिफाइंड बोल सकते हो, मतलब इसको तुम कुछ भी ले सकते हो. दिस इज फ्री वेरिएबल, है ना. और v2 और v3 के बीच में रिलेशन आ गया, तो वी कैन हैव वन वेक्टर एज 1,0,0। ठीक है, इसमें हमने क्या किया कि v1 को 1 ले लिया, we took v2 as let's say v3 as let's say 0, और another option can be उल्टा कर देते हैं, v1 को 0 ले लेते हैं and take v3 as 1, so that would give us as 0 minus 1,1. So we have two linearly independent vectors corresponding to lambda is equal to 1, or multiplicity was also 2 for this lambda is equal to 1. So we will have this matrix is a diagonalizable matrix. Okay.
Okay, sir.
Okay. Let's get something called as similar matrix. Okay. So in linear algebra, two matrices, let's say A and B, are called similar if there exists an invertible matrix P satisfying so A should be P into B into P inverse. So if you can find a matrix P such that you can write A as P times B into P inverse, then A and B matrix are called similar matrix. Okay. If you have two similar matrices, then you will have properties like they both will have same eigenvalues and those kind of things. Okay. So why I brought up similar matrices over here is there is one more definition of diagonalizable matrix. So if your matrix A is diagonalizable, then it is similar to a diagonal matrix D. ठीक है, what does that mean is अगर हमारा A जब भी diagonalizable होगा तो we can write it in this form, some Q times D into Q inverse. ठीक है, अब ये Q और D जो है ना, they are of some special type. So ये जो D मैट्रिक्स है, it's a diagonal matrix. Okay. उस डायगोनल मैट्रिक्स के जो डायगोनल एलिमेंट्स हैं, दोज आर नथिंग बट आइगन वैल्यूज ऑफ ए. ठीक है, और जो क्यू मैट्रिक्स है, क्यू मैट्रिक्स के कॉलम्स जो हैं, कॉलम्स आर आइगन वेक्टर्स कॉरस्पॉन्डिंग टू दोज आइगन वैल्यूज. सो यहाँ पे ऑर्डर थोड़ा सा इंपॉर्टेंट हो जाएगा. दैट इज कि अगर मान लो हम लोगों ने सबसे पहले लैम्डा 1 लिखा है, ठीक है, तो जो Q का जो फर्स्ट कॉलम होगा दैट शुड बी आइगन वेक्टर कॉरस्पॉन्डिंग टू लैम्डा 1 ओनली, देन यू विल गेट दिस काइंड ऑफ रिलेशन, राइट? एंड दिस काइंड ऑफ रिलेशन इज क्वाइट यूजफुल इन मेनी केसेस. ओके, सो वाज दिस क्लियर कि वी कैन राइट इट लाइक दिस? सो अगर हमारा A डायगोनलाइजेबल है तो हमें एक मैट्रिक्स Q मिलेगा, एक मैट्रिक्स D मिलेगा, जिसको कि हम इस फॉर्म में लिख सकते हैं. और D क्या होगा वो भी बता दिया मैंने, इट्स डायगोनल एंट्रीज विल बी नथिंग बट आइगन वैल्यूज, ठीक है, ऑफ दिस A मैट्रिक्स. ठीक है, जैसे पिछले केस में हमारा मान लो जो भी मैट्रिक्स था तो उसके लिए D बन जाता हमारा 1, 1, दूसरा क्या था 2, या ठीक है, बाकी सब 0. और Q मैट्रिक्स बन जाता तुम्हारा जो ये वेक्टर्स आए हमारे 1, 0, 0, और दूसरे पोजीशन पे आता 0, -1, 1, और फिर जो भी 2 के कॉरस्पॉन्डिंग आया था हमारा वो वाला v1, v3 था तो 1, 0, 1, और इधर सम Q इनवर्स, इसी का इनवर्स. ठीक है, तो ऐसे लिखने से फायदा क्या होता है, लेट्स से you want to evaluate some power of a matrix. Let's say your matrix is 4 cross 4 or 5 cross 5 or even very larger than this, and you need to, let's say, calculate a to the power 100. अब अगर हाथ से करने के लिए बैठेंगे, so it would be very difficult for us to calculate, right? So एक चीज देखो, if you have matrix, let's say diagonal matrix, let's say this is 1 2 3, let's take a 2D case only. The same thing holds for n cross n. Let's say this is 1 2 0 0. If you multiply it with the same, that is you are finding a square, then you will get what? This would be 1, this would be 0, this would be again 0, this would be 4. तो क्या हुआ, a स्क्वायर जब हम लोग निकाल रहे थे तो बस डायगोनल एलिमेंट्स के स्क्वायर हो गए, ठीक है. सिमिलरली इफ यू हैव अ डायगोनल मैट्रिक्स D, ठीक है, and if your D is equal to, let's say, D1 D2 Dn, this is a diagonal matrix, बाकी सब जगह 0, and you take D to the power n, then what you get is D1 to the power n, D2 to the power n, Dn to the power n, और बाकी जगह 0. So this is also a diagonal matrix with only diagonals power taken to the power n. Okay, so this is a property of a diagonal matrix, and we want to use this property to find like power of any arbitrary matrix that is diagonalizable. ठीक है, अब हमने क्या बोला था कि if we have A, then it can, if it is diagonalizable, then we can write it in form q d q inverse. So अगर हमें a square निकालना हो, so what it would be, q d q inverse, one more q d q inverse. So this becomes identity, and this becomes q d square q inverse. Okay, अब ऐसे ही अगर हम लोग चलते रहें, we will keep going. So what we can achieve is that a to the power n is q d to the power n q inverse. So rather than you have to multiply, let's say, a 100 times, what you can do is you can find its diagonal form. Okay, you can find its eigenvalue and eigenvector. q निकल गया, d निकल गया, q inverse निकल गया. Then d to the power n is very simple. You just need to raise those eigenvalues to the power 100, और फिर उसको इन मैट्रिक्स से मल्टीप्लाई कर दिया, you will get a to the power n. Okay, so this is a very good application for this thing, whatever we did, a diagonalizable property of a matrix. Okay. Was this clear?
Yes, sir.
Okay. और एक और जगह we can use this thing. So you have you heard of something called Taylor series expansion? So there are some Taylor series expansion for let's say 1 upon 1 plus x can be approximated very well by 1 minus x plus x square plus, say, minus x cube, and so on. So there are expansion for many functions you can do. So let's say rather than real number, you want to do such kind of approximation for, let's say, your matrices. ठीक है, तो अगर मान लो we have to do, let's say you want to calculate e to the power a, where a is some matrix, then how do we do that? Okay, तो वहां पे क्या करते हैं हम लोग कि we look at Taylor series expansion of e to the power x. ठीक है, तो मुझे अभी याद नहीं है Taylor series expansion e to the power x की, but let's say you want to find 1 upon 1 plus a. So here upon would mean inverse, so this is, you want to find 1 plus a inverse. Okay, int plus a inverse you want to find, that you can approximate by 1 minus x plus x square minus x cube, and so on. अब ये, because this is an infinite sum, you cannot keep on finding a and a square and a cube and then put it in this equation. If you use this kind of relation, that is your q d q inverse, that because if this is diagonalizable, then you can write it in this form, then you will get some pattern with respect to d. Let's say तुम्हारे जो diagonal के entries हैं, if they are less than 1, for I'm just taking an example, then eventually this thing will go to 0, right? So these kind of patterns you can make out over there, and you can say whether this series would converge for this thing or not, or those kind of things you can say. So you can see what is the Taylor series expansion for, let's say, e to the power x, and this is a very common way and like a useful way how we calculate e to the power some matrix. So you generally calculate e to the power some number, let's say 2, but how do you calculate e to the power a, or you can do more complex thing with matrix, there this kind of thing becomes useful. एक चीज बस अभी मैं बोल रहा हूँ, like I don't think this will be covered in this course. So even in the cases when you don't have like diagonalizable matrix, like your matrix is not diagonalizable, then you can find something as something called as Jordan canonical form. Okay. Those are not as good as your diagonalizable matrix, but one thing is that you can find Jordan canonical form for any matrix. Okay, so for this diagonalizable matrix, few matrices are diagonalizable, few are not. But for Jordan canonical form, you can find for any matrix, but they are not as good as like diagonalizable forms. So these also help you in computation when you try to take power. They are also of some special form. Okay, and they also help you in calculation. So I'm just mentioning it because if you like kind of somewhere encounter some problem where you have to take powers of matrix, but that is also not getting diagnosable, then you can look something like look at something like this in some book or somewhere, and you get reminded, yeah, that something can be done there. Okay. Okay. So yeah, one more thing that I wanted to mention is that these eigenvalues have some relationship with trace and determinant of a matrix. So first of all, what is trace of a matrix? Trace of a matrix is sum of its
Some of
diagonal elements.
diagonal element.
Yeah. Okay. So let's say you have matrix 1, 2, 3, 4. So its trace would be 5. Okay. So if you take sum of all your eigenvalues, okay, that is always equal to trace of that matrix. Okay, this is a proof property. Okay, and another thing is if you take product of these eigenvalues, then you will get it equal to the determinant of that particular matrix. I wanted to mention this, and yeah, probably this is a repetitive example. I won't solve this one. Okay, I'll go to this theorem, and then I'll try to solve this one. Let's see, or we might not even solve. Let's see. Okay. Now what it is saying is, let's say you have lambda 1, lambda 2, lambda m as distinct eigenvalues. Now remember when I said you, like if you have some eigenvalue with multiplicity only 1, you can just ignore that while checking diagonalizability, because I said they will be always like independent of others, and there always would exist a linearly independent eigenvector. So that guarantee I was able to give because of this theorem. Okay, so what does this say? This says that if you have distinct eigenvalues, let's say lambda 1, lambda 2, lambda m, and let's say you have a eigenvectors corresponding to them, that is v1, v2, vm, okay, are eigenvectors, then this set of eigenvectors are always linearly independent. Okay, we need to show this. Okay, how do we show linear independence of some vector? Okay, I think we can, there are like probably I can make out two ways to do this. I'll do one, and you can try other way of proving this just for fun, probably, or practicing. One way would be contradiction. So you assume that this is linearly dependent, and then you will get with some contradiction. And another way can be your something like, okay, let's see. I'll tell you another way when I'm doing it. You can try the contradiction method on your own. Okay, let's say how do we prove some set of vectors v1, v2, vn as linearly independent? What we say is that if a1, v1, if first thing is if a and vn is 0, then all my a1 is equal to a2 is equal to an must be 0. This is what we want to prove. Okay, so if you have to prove anything of form if this, then that, so how do you prove that? So in order to prove this, what you do is you assume this, that is, you assume whatever is here, and then you prove that, and then you prove whatever is here. Okay, so similarly over here, you let that this thing is equal to 0, and then using this and whatever is available to you, like whatever is given to you, you reach to a point where you can say that a1 is equal to a2 is equal to an is equal to 0. Okay, okay, so we have to prove that v1, va2, vm is linearly independent. Okay, so we let a1 v1 plus a2 v2 plus a3 v3 plus an vm is equal to 0. Okay, now what we can do is, okay, let's say vm is a eigenvector corresponding to lambda m. So this is what is mentioned to us, that vm is a eigenvector corresponding to lambda m. Let's take this operation both side, lambda m, we apply this operation on the both the side. Okay, because this is a linear transformation, then so if you have two things equal, if you apply some function or operation on both the sides, that would be same, right? So you apply p minus lambda I, this is lambda mi, on both sides. So what would the first entry give you? First one would give you t of a1 v1 minus lambda m times v1, and this is a1 is also there, into a1. Similarly, you will get till the last term. In the last term, what you will get is t of an vm plus an lambda m vm, and this term is equal to 0. There is a minus in here. Okay, now if we open the first term, what we get is, we can take a1 common from here, then this would be lambda 1 v1, because v1 is an eigenvector, minus lambda m v1. Similarly, for the second one, you get lambda 2 v2 minus lambda m v2. All the way here, here you get an lambda m vm minus lambda m vm is equal to 0. Okay, now this would give us as a1 v1 lambda 1 minus lambda m plus a2 v2 lambda 2 minus lambda m, and so on till an minus 1 vn minus 1 vm minus 1 lambda m minus 1 minus lambda m is equal to 0. Okay, now the second way that I was talking about was via principle of mathematical induction. Okay, how can we apply PMI on this is, we can apply PMI on number of eigenvalues. Okay, what do I mean by that is, so if you have only one eigenvector like this, let's say you had only one eigenvalue lambda 1 and correspondingly lambda 2, then this was already linearly independent. It is true for when your number of, let's say, this eigenvalue, let's denote it by k, that is equal to 1, then it is true. Okay, let's assume that it is true for k is equal to m minus 1. Okay, and then we are proving for k is equal to m. This is how you do in PMI. So now by PMI's assumption, this thing is already linearly independent, that your v1, v2, v of m minus 1, because they are m minus 1 in number, they are already linearly independent. So what that would mean is anything that is coming as a coefficient along with it should be 0. That is, these terms should be 0. So first one says that a1 into lambda 1 minus lambda m is equal to 0. Okay. Now your lambda 1 minus lambda m cannot be 0 because they are distinct eigenvectors. So what does this imply? a1 is equal to 0. Similarly, from the second one you can get a2 to be 0. Okay, and so on till a minus 1 you can get 0. Okay, now in order to get an to be 0, we just need to put everything in this equation over here. Then everything before this term would become 0. Sorry, you put it in this equation. Yeah, everything before this thing, not even this, you put it in this one. Yeah, sorry. So everything before this becomes 0. That will end up making an is equal to 0. Was it clear or a bit sketchy? I can repeat if it was not clear to you. Was it clear?
Yes, sir.
Okay, if it is clear, then it is fantastic. Okay. So again, we have a question. Probably I'll just pass my comments on how can we solve it. So you already know how we can solve for eigenvalues of A. We have done plenty of example. Find the maximum set S of linearly independent eigenvectors of A. So you just need to find eigenvectors and a linearly independent set. So for every eigenvalue, you will pick those many eigenvectors as you have your multiplicity if that many linearly independent exist. Now is A diagonalizable? That you can say if you have all your eigenvalues as real numbers in this case, and multiplicity is equal to the number of linearly independent eigenvector for every eigenvalue. Okay, and if yes, find such P such that P is equal to P inverse AP. So here this P, so what I said is that your A is equal to P dP inverse, then your P's columns are your eigenvectors. Okay, now what they have done is they have flipped this thing. So they have pre-multiplied by P inverse and then written P on this side. So this would become P inverse and P. So this would mean P inverse of AP is equal to D. So again, the way to find P is you have to write every element as columns, every eigenvector as columns of this matrix P. Okay, and probably I'll take a 2 cross 2 example so that the calculations are easy, and I'll show you how we can find such P. I'll take a very simple example probably. Okay. We had some 2 cross 2 example on the top. I'll pick one of them on. Yeah. Let's take this example. Why didn't it get pasted? It got pasted here. Okay. So we did this. I'm not sure what it. I'll just reconnect in a while. I think there is some problem with this one node. Yeah, I think that's okay. So this was the example that I solved initially. So we have a matrix A given, and we were asked to check whether this V1 and V2 are eigenvectors or not. We ended up finding that these two are indeed their eigenvectors. So, and with eigenvalues, I'll just calculate. So it is 1, 3, 4, 2, and this is 1 minus 1. So this would be minus 2, and this would be 2. So eigenvalue over here is minus 2, and the corresponding eigenvector is 1 comma minus 1. Okay. For the second one, this is 1, 3, 4, 2, 3, 4. So this is 3, 15. This is 12, 1, 8, 20. So this is with eigenvector 5. You can see this is 5 times 3, 4, right? And the eigenvector is 3 comma 4 in this case. Now what did I say is that you can write your matrix A as some P D T inverse, right? So how would you form P? P would be eigenvectors as column. So P would be 1 minus 1, 3, 4, okay. And your D would be eigenvalues on the diagonal positions, 0, okay. This is 0, 5. Now what is the inverse of this thing? So this goes here, this would be, I think, 5, this is 4, 1, and this is minus 3, 1, and the determinant is 4 plus 3, this is 1 by 7. I think this is the inverse. So 1 by 7, 4 minus 3, 1, 1, and this is 1, 3 minus 1, 4. Is this the inverse? This is 4 plus 3, this is 7. Yeah, 1 by 7 would give us 1, and this is 4 to the 12 minus 12, 0. Yeah, I think this is the inverse, right? So if you verify this thing, whether this thing is equal to A or not, we will just try to verify this thing. What I did is I wrote eigenvectors as column and eigenvalues as my diagonal elements. Okay, so let's take 1 by 7 out and let's do this multiplication. This would give me 1 times minus 2, this is minus 2, right? This is 15, this is 2, and this is 20. Okay, and then I have to multiply with 4 minus 3, 1, 1. Let's see what we get. This is 1 by 7. This is minus 8 plus 15. This is 7. This is minus 6 plus 15. So minus 6 plus 15 is 9. No, what it is? This is 6 plus 15 is 21. This is 8 plus 20 is 28. This is minus 6 plus 20, it's 14. So if I divide by 7, what do I get? This is 1, 3, 4, 2. Was this my matrix? Yeah. This was indeed the matrix that we began with. So this was just to verify the claim that I was saying. Okay. So you can find P by just taking the eigenvectors as columns and your D matrix by taking diagonal entries as your eigenvalues. Okay. Anything else you want to ask related to this eigenvalues and eigenvectors? Any doubts you guys have?
No, sir, all clear.